Today I'm presenting our work, a tiny change, a giant leap, long-tailed class-incremental learning via geometric prototype alignment. Let's start with the problem we tackle. Long-tailed class-incremental learning, or LTCIL. Imagine a model that needs to learn new classes continuously from a stream of data, like a wildlife monitoring system identifying new species over time. This is class-incremental learning. Now, real-world data is often long-tailed, meaning a few head classes have many examples, while many tail classes have very few. LTCIL combines these two challenges, learning new classes sequentially without revisiting old data under this severe class imbalance. The goal is to minimize catastrophic forgetting of old classes while simultaneously boosting the performance on underrepresented tail classes. Existing methods often use memory replay or loss reweighting, but they overlook a critical issue, which is the geometric misalignment in the classifier. Let's look at Figure 1. On the left, with random initialization, the classifier weights are misaligned with the actual feature distributions. This causes two harmful forms of gradient competition, one between new and old classes, and another between head and tail classes. Head classes, with more samples, dominate the gradient updates, suppressing the learning of tail classes and leading to unstable training. This is the core problem we identified. Our key insight is simple but powerful. If we can initialize the classifier correctly based on the feature geometry, we can prevent this misalignment from the very beginning. This leads us to our main contributions. 1. We are the first to formally identify and analyze the problem of gradient competition caused by classifier misinitialization in LTCIL. 2. We propose a novel geometric prototype alignment (GPA) method, which provides a geometrically optimal initialization with Fisher discriminate guarantees. 3. Our solution is a plug-and-play module that can be easily integrated into most existing CIL frameworks with just a few lines of code. 4. Through extensive experiments, we show that GPA brings substantial and consistent improvements, establishing a new state-of-the-art on multiple benchmarks. Now, how does GPA work? Our methodology is elegant and consists of three clear phases. First, frozen prototype estimation. When new classes arrive, we use the frozen feature extractor from the previous session to compute a prototype, or a centroid, for each new class. This gives us a reliable geometric anchor in the feature space without distorting previously learned knowledge. Second, geometric weight initialization. This is the tiny change that makes the giant leap. Instead of random initialization, we initialize the classifier's weight vectors by directly aligning them with these computed prototypes and projecting them onto a unit hypersphere. This simple step decouples the feature magnitude, which is often smaller for tail classes, from the angular discriminability, creating a balanced and well-structured starting point for the classifier. Third, dynamic anchoring optimization. During incremental training, the feature distributions naturally drift. To maintain geometric consistency, we introduce a dynamic anchoring loss that gently pulls the classifier weights towards the evolving prototypes. This ensures the model remains stable for old classes while being plastic enough for new ones. In essence, we synchronize the classifier with the underlying geometry of the feature space throughout the entire learning process. The results speak for themselves. We integrated our GPA module into 10 representative CIL methods. As you can see in the main results table, GPA brings consistent and significant improvements across all methods and datasets. For example, on SAFAR 100LT, GPA boosts the average incremental accuracy by up to 10.75%. More importantly, it specifically enhances tail class performance. Our method narrows the performance gap between head and tail classes by up to 18.6%, demonstrating its effectiveness in tackling the core issue of imbalance. Furthermore, GPA effectively reduces catastrophic forgetting. As shown in the results, it lowers the average forgetting rate by 6.38%, proving that better initialization leads to more stable lifelong learning. In terms of implementation, GPA is incredibly simple. As the pseudocode shows, it can be integrated with less than 10 lines of code, making it a very practical and low-cost addition to existing systems. Finally, let's look at Figure 6, which provides a theoretical validation. This figure shows the convergence acceleration achieved by GPA. Because we start from a geometrically optimal point, our model converges much faster, reaching the same accuracy in nearly half the number of epochs compared to random initialization. This not only saves computation, but also leads to a better final solution. To conclude, we identified a fundamental geometric problem in long-tailed class-incremental learning. Our proposed solution, geometric prototype alignment, acts as a small but powerful plugin that corrects classifier misalignment, leading to faster convergence, less forgetting, and dramatically improved performance on tail classes. It's a simple change that enables a giant leap forward for continual learning systems in the real world. Thank you.